Welcome to homework.
71 from the Smith Organic Chemistry textbook. And this problem says low molecular weight esters often have characteristic odors. Using its molecular formula and proton NMR spectral data, identify each ester. And so we're given compounds R and S. We're given NMR peaks for each of them. And we're given a formula for each of them, and it's actually the same molecular formula. And so I'm going to calculate the degrees of unsaturation to get started. And fortunately, we only have to do this once since it is the exact same molecular. So the HDI here is going to be equal to 2 times 7 plus 2. Oh, there we go. Plus 2 minus 14. And all of that is going to be over 2. And so this comes out to 2 over 2, or 1. So 1 degree of unsaturation in each of these molecules. And since obviously the problem tells us that these are esters, the carbonyl of the ester is going to account for that single degree of unsaturation in both of these cases. So there's not going to be any other double bonds or any rings in either of these molecules. So then the next thing to do is to look at the NMR data and try to identify which peaks are what here. And so we have a signal at 0.93 ppms. It's split to a doublet, and it integrates to 6 protons. So this is going to be 2 methyl groups, 2 identical methyl groups. So they are both on the same carbon. And so just looking down the signals, this signal at 1.69 ppm is split to a multiplet, and it integrates to 1. So this is very probably a tertiary carbon. So a carbon with just 1 hydrogen on it and 3 bonds to other things. And since our 2 methyl groups are split to a doublet, that signal split to a doublet, I am going to say that they're both attached to the carbon that has the proton that's accounting for this signal at 1.69 ppms. So basically, one side of our molecule is going to look like this. So 2 methyl groups on the same carbon, and that carbon is going to have 1 other bond, and then there will be a proton on that carbon as well, and that proton is this one right here, is what's giving us this signal. So then looking at the rest of these signals here, we have another methyl group here, the signal at 2.04 ppm. That's going to be another methyl group. And then it looks like 2 methylene groups here and here. So these 2 signals are from methylene groups. Okay. And so our furthest downfield signal at 4.1 ppm is split to a triplet and has an integration of 2. And so I am going to say that that is the methylene group that is attached to the ester oxygen, which is why it's so far downfield. It's split to a triplet, so it only is going to have 1 neighbor. Okay. Looking at what else we have. Oh, okay, here we go. So we have a methyl group that is a singlet. So that's going to be directly attached to the other side of our carbonyl. So this methyl group is going to be like this. Okay, so we have this piece now. And then we have these 2 methylene groups that, as I said, we just need to account for. And so the 1 is going to be the furthest downfield one is split to a triplet. So that's going to be directly attached to that oxygen. And then the next methylene group is split to a multiplet because there are things to either side of it. Okay, and then we will have. Okay, and then we'll have the rest of the molecule that we drew here. So 1, 2, 3, 4, 5, 6, 7. Okay. 1, 2, 3, 4, 5, 6, 7. Yep. Okay, so there we go. That's the structure here. Let me redraw it a little bigger. Okay. And so just to get an idea of what we're talking about here, so the green arrowed proton, the third signal there is going to be the proton that is on the carbon here. Our 2 methyl groups here, which I'm arrowing in red, are going to be here and here. Our 2 methylene groups, so this one is going to be right here, and we know that because that one is the multiplet. And so the other one here, come on. Okay, and this other one here that's split into a nice triplet is going to be this guy right here, and then obviously the other methyl group is this methyl group on the other side of the molecule, the other side of the ester. Okay, so we're going to do the exact same thing for this molecule S, which we're told is the aroma of rum. And so again, the HDI, we already calculated it. We don't need to go through calculating it again. It's 1, and that 1 is going to be encompassed by our ester carbonyl. And so we'll just do the exact same thing here. So again, our first signal integrates to 6. So this is, again, going to be 2 methyl groups. Oh, man. Apologize. I don't know why I am experiencing this awful lag. So there we go. 2 CH3s. So then immediately below that at 1.15 ppm, we have a triplet that also integrates to 3. So we'll go ahead and make that another methyl group. Come on. There we go. And then we have this multiplet at 1.91 ppm. It integrates to 1. So again, this is going to be a tertiary carbon. So that part of this molecule is going to be the same as for molecule R on the previous page. We're going to have those 2 methyl groups coming off of this carbon with 1 proton on it, which is where that third signal comes from. And then our signals at 2.33 ppm and 3.86 ppm are going to be methylene groups again. So that's a methylene, and this is a methylene. So the pieces of this molecule S are exactly the same as the pieces of molecule R, but they are connected in a different way. And so we can, once again, start with the right side of the molecule. So we have these 2 methyl groups coming from a tertiary carbon with 1 proton on it. And so that takes care of our first signal and our third signal. So looking at the second signal, we have a methyl group that's split to a triplet this time, which means that it has a methylene group next to it. And so our fourth signal is a methylene group that is split to a quartet. So it's next to a methyl group. And so putting those 2 pieces together, So the other side of our molecule this time is going to be a methyl group attached to a methylene group. And I'm going to say that since that methylene group is split nicely just to a quartet, it only has neighbors on that one side where the methyl group is. Okay, and our other methylene group is split to a doublet and is pretty far downfield. So I'm going to say that is directly attached to the oxygen here. So there we go. Yeah. Okay. And so that's what we have here. And I'm going to arrow these as I like to do to hopefully try to help anybody who may not see exactly what I'm talking about where everything is. So there's those two methyl groups. Here is the proton on that tertiary carbon. It's going to be right there. So then next, we have a methylene group that is just split to a doublet and is far downfield. So that's going to be this guy that I'm arrowing in blue. And we know that because it's split to a doublet, so it only has one neighbor. And this is really the only way that we can configure this, that would be the case. And then here in black, we have the other methylene group split to a quartet, which means it has a methyl group for a neighbor. And so there's that. And obviously it has the methyl group for the neighbor there. And then the other methyl group, pretty explanatory. I'll do this one in green too, since I do only have 4 colors to work with. So there's that other methyl group. And so that's the answer for molecule S. And so, I think that's really the only way to solve this problem is to try to figure out what piece of the molecule each of these signals represents, and then just put the pieces together. And we can use the splitting patterns to tell us about the connectivity of these pieces. And so, again, that's the answer to chapter 14, problem number 71.